In this video, I'm going to talk about atomic spectra. And before we do that, we have to talk a little bit about the electromagnetic spectrum. So the electromagnetic spectrum is just the different wavelengths of light, where the wavelengths will correspond to different energies of the light. So for instance, radio waves, these are low in energy, they're low frequency, and they have long wavelengths, where gamma rays are high energy, high frequency, and have short wavelengths. And so these two equations here tell us the relationship between the wavelength, the frequency, and the energy, where this first one is telling us that the frequency multiplied by the wavelength is equal to a constant, and in fact that constant is the speed of light. And that means they must be inversely proportional to one another, because if we multiply them, we always have to get the same answer. So that means if one of them is getting bigger, the other one has to get smaller in order to get the same answer. Then this second equation here is telling us that the energy and the wavelength of light are inversely proportional. So as one of them increases, the other decreases. And since we said that the wavelength and the frequency are inversely proportional to each other, that must mean that the energy and the frequency are directly proportional to each other. So as energy increases, the frequency increases, and vice versa. And this means that as wavelength increases, frequency and energy decrease. That as wavelength decreases, frequency and energy increase. So for instance, we can start with our low energy, low frequency, long wavelength here. Then as we increase energy, increase frequency, and decrease wavelength, as we go from left to right across the spectrum, we get to the high energy, high frequency, short wavelength over here. And what's important about that for our purposes is that the elements give off discrete atomic spectra of light. So remember, these different colors correspond to different energies, and these different energies that correspond to what the actual element is. And this also gives rise to the different signature colors that these elements give off when we pass a current through them. So you may have heard of things like neon lights. So you can do this with other gases as well, and they will give off these different colors. So it gives off this single color that we see with our eyes. You can actually buy pretty cheap little instruments that if you look at these through it, you can actually see their atomic spectra that look like this. But what this tells us is that because we have these discrete atomic spectra for the elements, this confirmed the electrons are in discrete energy levels around the nucleus. Because remember, those different colors in our spectrum here, those correspond to different energies, so we must have different energy levels for our electrons around the nucleus. And these energy levels of electrons are what are called principal quantum numbers. These are whole numbers starting at 1, which is the lowest energy level, and then all the other ones correspond to the rows on the periodic table, going up to 7, which remember is our bottom row on the periodic table. And so this gives rise to the Bohr model of the atom, which is a nucleus that has these different orbits for the electrons, where the orbits correspond to the energy levels of the electrons. So that gives rise, like I said, to the Bohr model, where we have the first energy level, and this can hold 2 electrons. We'll talk a little bit more about the number of electrons that these different orbits can hold in the next video. But for now, just know that they have different numbers of electrons that the different orbits can actually hold. So energy level 1 can hold 2 electrons, energy level 2, 8, energy level 3, 18, energy level 4, 32, 5 is 50, 6 is 72, and 7 is 98 electrons. And so, like I said, we have these discrete orbits, which means that you cannot have an electron orbiting somewhere between these two energy levels. It has to be either at one or the other. And so that gives us rise to that discrete energy levels, which we will see here is how it gives rise to the discrete colors given off in their spectra. So we can think about it this way. So if we start with our proton right here, then we want to start adding these energy levels around it. So we can add 1, and over here on the left, I'm showing this in a common energy level diagram that we'll be using throughout this video. So this corresponds to the first energy level, second, third, fourth, and fifth. We could go up to 6th and 7th, but just because of space here, I'm only going to go up to 5. And so like I said, this one is the first energy level, the second energy level, third, fourth, and fifth. And then we can put our electron here. So we see that over on the right, we have that electron orbiting in that first energy level. And so we can put this electron right here in our other diagram on the left. And that is the diagram I will be using for this video. And so if we have a photon coming in, it's going to come at this electron, which is in that lowest energy level. And when it does, that electron will absorb it, and that will actually move it to that higher energy level. So remember, these photons have energy depending on what wavelength they have. And so when a certain wavelength of light hits this electron, it will promote it to that next higher energy level, where that energy level corresponds to the wavelength of light that actually hits it. And then when it re-emits that electron, the electron will relax back down to that lower energy level and give off that light, which then can be detected and shown in that spectrum. Then if we have a higher energy photon come and hit this electron and get absorbed, it will move up to an even higher energy level. So now instead of going to energy level 2, it's going to energy level 3. And so then when it re-emits that, it will fall back down to the first energy level, and we can then detect that higher energy photon that comes off of it. And so that is what's happening during this absorption and emission. We can also look at it this way if we want to just use our atomic model. So remember, we have the photon hitting the electron, it absorbs it, moves to a higher energy level, then it releases that photon and relaxes back down to a lower energy level. And what we see is because we have these differences in energy levels, so it can go from 1 to 2 or 1 to 3 and so forth, and it can go from 3 to 2 and 3 to 1 and so forth. That's where we end up getting these different energies in our spectra, these different colors in our spectra. And that explains why we get these regular discrete energy levels for different atoms. So for instance, for the hydrogen atom, the differences in energy levels can be calculated using what's called the Rydberg formula. And so this just shows that the difference in energy, this delta E here, is equal to this constant multiplied by 1 over the final energy level minus 1 over the initial energy level. So this will tell us the difference in energy levels between, say, whatever final is. So say that was n equals 2, and then the initial one, which is n equals 1. So if you plug 2 and 1 into the n's for this equation, that would tell you the energy difference between those two energy levels. And so what we see, like I said, we can have these differences between each of the different ones. So for instance, from this n equals 1, we can go from 2, 3, 4, 5, 6, and 7, or we could go from 3, 4, 5, 6, and 7 down to 2, or 4, 5, 6, and 7 down to 3, and so on. And for the hydrogen atom, they have these different names for it. What we see in our hydrogen spectrum in the visible light is actually from what's called the Balmer series here. So that's going down to the second energy level, and so that's what shows up in the spectrum shown down here at the bottom. Whereas things like the Lyman series, we see that those are very large differences in energy, so those would give off very high energy photons that would be sort of in the ultraviolet and higher range. Where these other ones up here, the Passion series and the Bracket series, would be even lower energy, so those would be in the infrared and lower energy levels. So those would not be visible to us. And so what's interesting about this is that each element has its own unique difference in energy levels for its electrons. So in other words, the energy difference between, say, n equals 1 and n equals 2 is not the same for hydrogen as it is for helium, and the same would go for all the other elements. And also, the energy for each level are also different in absolute terms. For example, the ground state energy in hydrogen is higher in energy than the ground state energy in helium. And that looks like this. So these are actually the energy levels for hydrogen and helium. What we see is that this difference from n equals 1 to n equals 2 in hydrogen is smaller than that difference in n equals 1 to n equals 2 in helium. But also, the difference in the ground state energy level for hydrogen and helium looks like this, where for hydrogen it's higher in energy than it is for the helium. And this means that different elements absorb and emit photons at different wavelengths, which we saw in that spectrum earlier. This essentially gives each element a fingerprint of which wavelengths of light it absorbs and emits. These fingerprints can be seen in their atomic spectra, and the atomic spectra can then be used to actually identify which elements are present. Remember, these spectra are kind of like fingerprints. So just like a fingerprint can be used to identify a person, we can actually use these spectra to identify the elements. So if we have databases of these spectra, which scientists actually do, if we take some spectra of an unknown, we can then compare it to the database and come up with which element this must be. So for instance, if we have this unknown down here, we compare it to all these other spectra up here, and we see that it corresponds to the mercury. So that would mean that we know that we have mercury present in our sample. And these differences in the colors given off by these spectra are also what are used in fireworks. So the different elements are used in different fireworks to give the fireworks their different colors. So for instance, red fireworks often have strontium salts, orange calcium salts, yellow sodium, green barium, and so on and so forth. So the fact that these different elements give off these different colors can be used, for instance, in making fireworks. But for chemistry, like I said, the thing we're interested in is that these can act like fingerprints, which can actually be used to identify different elements. And in fact, that's what, for instance, astronomers do when they're trying to come up with what sorts of things are in the atmosphere of another planet. They can use the light passing through it, which will then emit in these different discrete spectra, and they can use that like fingerprints to actually identify what elements are present in the atmosphere of other planets. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.